So welcome to part 3 of lecture 9. In this part, I kind of want to just pause here and just kind of highlight what we're going to be doing before we get into the details. So we have this set LVW, which consists of all linear maps from V to W. So far it just has it's just a collection of functions. But what we're going to do in this part of today's lecture is show that this set actually has more structure. It actually has the structure of being a vector space itself. So for it to be a vector space, we have to show what the additive operation is. How do we add to the elements inside of the set, and how do we do scalar multiplication? So I want to keep that in mind as we go on. Is what we're trying to do is show that this set of functions can actually be given extra structure as a vector space. So how do we do that? Well, we can define operations on L L, which is all the set of functions from linear maps from V to W, as follows. Suppose that I take two of these linear maps and a scalar and f, and what we're going to do is we're going to define a new function, s plus t, and so this is going to be a function from V to W, and we're going to define it by taking an element in V, and we're going to send it to the sum of the elements that we get when we plug in V into S and V into T. So these are elements in W, and so we can add them over together, and that's what we're going to send our function to, or send our element to. And similarly, we're going to take lambda times S to be the function that we get by taking a vector V, first evaluating it evaluating it as, so we get a vector in W, and then multiplying that by the scalar lambda. Okay, and we're going to give both of these guys names. We're going to call S plus T the sum, and we're going to call lambda S the scalar product. Okay, and these are new functions. They're totally legitimate functions. But what you need to show is that the following property holds: is that when you build these new functions, that the sum and the scalar product are also linear maps. So that means that s plus t and lambda s belong to this set of linear maps from V to W. Now it's not hard to check that these new functions are linear maps, and I'm going to leave that for you to convince yourself, or you could go see in the textbook. So what that means, though, is that we've now taken this collection of functions or linear maps from V to W, and we've given it a sum operation, an additive operation, and a scalar multiplication operation. And now we can check whether with these operations we've turned it into a vector space. And that's actually what the next theorem states, is that this set here of linear maps is actually also a vector space with these operations. Okay, so now I'm not going to check all the properties. I'll show you some of the properties, right? So the zero vector, okay, is the zero map that we defined in the first part of today's lecture. So it's the zero map, right, which is given from V to W, given by 0 times V is equal to 0, or 0, V evaluated at 0 is the 0 element. So remember, this map belongs inside of this set, and it's going to play the role of the 0 vector. Okay, so the 0 vector is the 0 map between the two. Okay, what about like the additive inverse, right? So let's take some function V in W. Well, then negative t, we can define negative t to be the map from V to W is the function that's given by negative t v is equal to the negative of the output. So it takes the original function, plugs in v, and then returns the negative inside of w of that value. So you're getting a new function, and this is a linear map. Okay, this is a linear map. So negative t is inside of the set of all linear maps from v to w. And it plays the role of the additive inverse, right? But then if we take t plus the negative of t and we evaluate this new function at v, we get tv plus the negative of tv, which is equal to 0 for all v in v. So this function, t plus negative t, is equal to the 0 function, or the 0 map. So same as the 0 map. Okay, so there we kind of proved that every element in T would have an inverse, okay, with respect to the operation of addition. And the other, oops, fix that. And let me just say that you can convince yourself that the other properties hold. I'm not going to go through them all, but you can convince yourself that all the other properties hold. So it takes a little bit of kind of getting used to thinking about what this set is, right? It's a set of functions, but the functions themselves are the vectors. So you're normally used to thinking of vectors as being tuples or polynomials, but now we're thinking of our vectors being functions themselves. So this is going to be a vector space, okay? And so I think I wrote this at the bottom, is that what happens now is from any two vector spaces V and W, you can create a new vector space coming from all the linear transformations between V and W. So at the beginning of today's lecture, I said what we have is first we're introducing objects, and then we want to look at maps between the objects, which is this set here. And in the case of linear algebra, we actually end up creating, if we look at the collection of all those maps, we end up creating a new vector space. And somehow this vector space here gives us information about the V and W. So in the last part, I kind of want to connect this back up to some of the stuff that we did in Math 1B03, which will help kind of reinforce some of these ideas.